Okay, welcome at our final presentation talking about the mainframe and data center trends and the future. So, title of this presentation is Beyond the Mainframe, Data Center Trends. First, we want to look back and identify some trends. And if you look at this old classification, you see the SISD, SIMD, MISD, and MIMD systems classification by Flynn from 1966. But basically, we distinguish between uniprocessors, the classical von Neumann computer, and vector and array processors, which are power computers today. Then we have the entire world of multiprocessors, distributed systems, and we have the pipelining as a concept that we see in all the instruction sets today as well. So basically, we can notice that all the systems that we see today are either SIMD or MIMD systems. And if you look at MIMD systems, then you see similarities to standard multi-core, many-core systems today. You may have shared memory with a close coupling. You may have shared disks with RAID systems, or you may have so-called shared nothing systems. So most systems today are still closely coupled, but there's a clear trend towards distributed systems with fewer coupling facilities. The mainframe belongs in the category of the closely coupled systems. There's another aspect, and this is often called a NUMA problem, so the non-uniform memory access problem, that systems are built out of components, and while for a long time the hardware kept the impression that the components are all ordered and accessed in a quite regular fashion, this abstraction is no longer maintained by today's hardware. So we have NUMA characteristics, which means that some parts of the memory are quicker accessible from a processor than other parts of the memory that are closer to other processors. So memory and processing units are getting co-located, and this has implication on the speed of execution if you organize your programs not correctly. One more look into the history and into the textbook, basically, with the sequence symmetry, which was a classical example for a system that is well balanced, that is symmetric, in the sense that all the processors have the same access paths to memory. We have a bus infrastructure and so forth. So well-balanced system, classical MIMD computer. And then we see another example that became quite famous, which is the Intel Paragon. It was not terribly successful in a commercial sense. However, it was a milestone in the sense that it consisted of many nodes, and each node was running its own operating system's instance. In that case, that was the Mach operating system. But this is an indication that systems getting closer to clusters or distributed systems in today's world, closer than to classical SIMD or MIMD systems. And there's actually an entire trend which is called rack scale computing, which indicates that future architectures are going to be built in that fashion. So we are talking about scaling, and scaling happens in scale-out scenarios, basically addressing more than one computer, addressing an entire rack. But scaling also happens in scale-up scenarios where computers getting more compact, more dense, where we still look at standard architectures, where multi-core and multi-threading are key features. And we look at standard operating systems with virtualization and trustworthiness and security clustering as key attributes. Turns out these systems, they need new programming models. They need, we look at software architectures, we look at services. So there's a trend that architectural principles that have been exercised in the mainframe world for a long time, that they arrive at standard architectures, at commodity servers today, and need to be addressed by the software as well. And then there's one other problem that is well known to the mainframe people, but also largely ignored by the mainframe people, because these systems have one objective, and this is zero downtime. If you look at other optimization criteria, then energy consumption comes into play. And what we see here is a screenshot actually from an onboard administration console and a blade system, where we are able to put power caps on the power units, and that way restricting the energy consumption of the entire computer. So this is actually an open research question. How should you structure your programs? How should you place your workload so that the energy consumption in a data center is minimized? And along that line comes the term of green IT, where we look at consolidation and we try to increase the efficiency of program execution. And you can only optimize what you can measure. So the first initial question is, how would you measure energy consumption of your programs? So if you look at your programming language, then you will figure out that there's no such keyword like power consumption or energy consumption in the language. So it has to be somewhere in between. It's a non-functional property, but it needs to be added to systems in the future. Next aspect, going from zero downtime, what the mainframe stands for, to more commoditized server systems, we still talk about dependability. And dependability means that we have certain trustworthiness that a computer system works reliable. And the question always is, how can we deal with unexpected events? And these events, they impact cost and performance of a system. We need maybe to replicate units. We need to take measures for fault prevention and fault removal. We need to look at the source code and put efforts into software engineering, but also it's a question of system architecture in the data center. And there are examples like the left-hand side where we have the hardware solution. We look at mission-critical systems, and if it comes to human life, no price is too high. This is the place for the mainframe, and still will be the place for the mainframe for a long time. But then we have also large-scale clusters and distributed systems and these many-core servers, where we want to optimize for both, for performance and cost, but also to some extent at least for dependability. So what is the unit of failure, of problem, basically? Another aspect, if you look at commodity servers, this is the introduction of accelerators, of additional functional units that are no longer CPUs, but maybe GPUs or FPGAs that bring additional compute capacity to the table, but somehow need to be added into the infrastructure. And this can be done via interfaces like the PCI Express bus, for instance, or it can be done in a cache-coherent manner. So the seamless integration of accelerators is another trend that we see in the data center. And the mainframe is actually not a very good example for integrating accelerators if it comes to additional functional units. If it comes to enriching the instruction set and building additional functionality on a processor, then the mainframe is the prime example for implementing Java application processors, for implementing crypto units and having extensions to the instruction set. So the message here, while mainframe tries to integrate everything into a single box, the trend in the commodity servers is rather that we keep adding additional functional units. And this goes quite a way. What we see here is a screenshot of the structure of a silicon graphics systems that we actually have in the building, where we see that besides the inner quick path interconnect, which is the prime link here, interconnecting these structures of four, basically blades, 4 sockets, to a more dense interconnection network. And there is a directory-based cache coherency protocol in place. There are third-party interconnection technologies in place. So rack scale computing, a future trend in the data center. And besides the mainframe, there's another system, this is worthwhile mentioning, which would be IBM Power. Also a little exotic in comparison to the ubiquitous Intel architecture. However, a system that inherits many attributes from the mainframe in terms of high availability, in terms of maintainability and serviceability. And these are also great scale-up systems like depicted here on the screen. The Power architecture is interesting because they have a special approach towards integrating accelerators with the computer. As I mentioned, nothing gets close to the mainframe where we just integrate or keep integrating in the instruction set additional capabilities. But with Power there is CAPI, and CAPI is the Coherent Accelerator Processor Interface, where the idea is that we have a cache-coherent integration of accelerator units like GPU or FPGA with the processor. And then we figure that problems occur in software more and more, and that we have additional fault classes, that we have less error containment if it comes to software. If you look from an HPC, high-performance computing perspective, it might even be as bad that an entire system, entire computation breaks down if a single node breaks. In more throughput-oriented workloads, we oftentimes have a little better error containment, but typically if a system fails, quite a significant amount of the system is going to fail. So the traditional hardware models need an update. We have memory with increased density and with higher data rates. Instead of cores, or we use many cores instead of a simple monolithic processor. We have the interconnect, which actually might be a source for contention and a source for problems, which is crucial if it comes to fault isolation. If we look at reactive fault tolerance, that might get inappropriate. Also an area where we can learn from the mainframe operating systems. If you look, for instance, at the ZOS, there you have these predictive fault tolerance measures. And also systems do not really scale very well. We have additional software layers like the virtualization layer, which has been there for a long time in the mainframe world, but is relatively new to the table in the classical Intel-based data center. And we have relatively weak tool sets if it comes to reliability research. Here at the Hasso-Plattner Institute, we have the Future SOC Lab, which is collaboration with industry partners for looking at next generation x86, x64 hardware. It is active research work where we want to understand new fault classes, where we want to do failure prediction, where we want to look at active, proactive virtual machine integration. This is actually a lab that hosts many of these research projects, not only from our institute, but it's open to the entire world, basically. And I just want to mention a few details from one project, which looks at failure prediction on several layers. On the CPU level, we want to look at online hardware failure prediction, which means performance counters. These are available in all the major architectures. You can also look at performance counters if it comes to memory, and this is actually an interesting incident here where we see that a memory module failure was predicted in a couple of years ago already, but 20 minutes basically before the actual failure happened. And talking about the problem size, this unit was 16 gigabyte of memory. So it's not just a few memory cells or a few bits, but huge amount of memory that fails. I mentioned the ZOS as an example where we have predictive failure analysis and runtime diagnostics built into the ZOS. So operating systems need to be extended, and I mentioned Power, where we have AIX with a couple of these features, but we're also seeing these features showing up in the Linux operating system. And then there's an entire new field that receives much attention today, which is machine learning and data science. And probably the vision is that we could do fault prediction by applying machine learning to all the aspects, like to the hardware where we have failure predictors, to the virtual machine monitor, to the operating system, but also to the application and the middleware. That way we can factor in domain-specific knowledge. It will be pluggable so that it's adaptable to different use cases and so forth. And the vision then is building such a system health indicator as outcome as a result of a multi-level failure prediction, and the system health indicator would trigger virtual machine migration so that we can migrate away from a server system before problems manifest in the application. All right, system health indicator. And with that approach, we can draw a couple of conclusions. So we see that there are advances in server technology. We have an ever-growing number of CPU cores. Systems are getting more and more dense. We have tremendous amounts of memory today, and there is non-volatile memory showing up on the horizon, which actually might bring new problems to the table, because the typical approach to solve a problem by just rebooting and redoing the thing will no longer work if you have non-volatile memory. Also, we noticed that reliability becomes a key quality attribute. This is something we take away from the mainframe. However, with these high level of integration and the shrinking structure sizes like 22 or 14 nanometers, or even 7 nanometers in the future, we will see multi-bit errors instead of just a single bit flip. So we need new measures for fault tolerance and error correction. And as I suggested, fault prediction, dynamic reconfiguration, where we see examples in all the major systems, they may provide new solutions. And isolation against fault propagation, we know the LPAR as the ultimate means of isolation in the mainframe. In the commodity server, it would correspond or would translate into blades. You just place your workload across several nodes. And then there is also new programming models showing up, like the microservice architecture, which became famous with Netflix and their chaos monkeys, where they, while operating, just kill service instances to show and to see and to be sure that the system has the desired self-healing capabilities. So in the end, we see again that the computer architecture drives changes in system software on several levels. And that starts on the left, where we see that the servers have evolved to new form factors, higher density. We see advances in the operating system, like virtualization and trustworthiness, security, like clustering. We see new problems coming up with virtualization, by the way, like the so-called blue pill attack. So how can you basically tell whether somebody has placed a virtualization layer between you and your hardware and makes changes to the operation of the hardware? We also see, and that started with cloud computing, that people don't want to buy big systems anymore, but they want to follow the pay-as-you-go scheme. So you need to provide additional hardware and have a model for pricing to price or to have the customer pay only if the hardware is being used. And then I mentioned already the GPU and the FPGA. So we see an entire world of hybrid computing where there is more than just the CPU as a processing model. And OpenCL is one of the new programming models, CUDA another model, but there's more to come. And I also mentioned already the CAPI and OpenCAPI, which got introduced with Power, where the idea is that everything gets in a homogeneous fashion again by implementing cache-coherent interfaces. So an entire world of changes. Some of these changes are visible in mainframe today already, but some of them also are driven by price optimization, TCO optimization goals, and they will not be visible in the mainframe that much, but are more important in the commodity data center today. In the end, the mainframe still defines the gold standard for the data center. Thank you for your attention. That concludes the course.